Imagine two twin brothers born on the same day. However, when one of them decides to travel through space in a spacecraft moving at nearly the speed of light, something surprising happens. While the traveling twin journeys through the stars, time passes much more slowly for him than for the brother who stayed on Earth. When the traveler returns, he looks young, while his brother has aged considerably. This fascinating phenomenon is known as the twin paradox, one of the most intriguing concepts in Einstein's theory of relativity. But how is this possible? How can time pass differently for people born at the same moment? And why, upon returning, does the traveler find that only a few years have passed for him, while decades have passed on Earth? The answer lies in modern physics, specifically in Einstein's special relativity. In this video, we will delve deeply into the twin paradox, explore what science has to say about the passage of time, and discover why this idea is not just science fiction but a fascinating reality of physics. Get ready for a journey through time and space. The twin paradox is a compelling way to illustrate time dilation, a phenomenon predicted by Albert Einstein's special theory of relativity. To better understand it, imagine two identical twins of the same age. One remains on Earth, while the other embarks on a space journey in a ship moving at a speed very close to the speed of light. According to the theory, time doesn't pass the same way for both. For the twin who remains on Earth, time flows normally, according to what we call absolute time. However, for the twin traveling at high speed, time passes differently. It dilates. This means that for the traveler, time passes more slowly compared to his brother on Earth. This phenomenon occurs due to the relationship between speed and time. The faster someone moves, especially at speeds close to the speed of light, the slower time passes for that person relative to someone at rest. So, when the traveling twin returns to Earth after his journey, he finds his brother much older than him. While only a few years may have passed for the traveler, decades might have passed on Earth. This paradox is so named because it challenges our intuition. We expect time to be the same for everyone, no matter where or how fast we're moving. But the twin paradox shows that time is relative, shattering the notion that time is absolute and unchangeable. Albert Einstein's special relativity formulated in 1905, is the theoretical foundation that explains the twin paradox. According to this theory, the laws of physics are the same for all observers, regardless of their state of motion, as long as they are not accelerating. Even more crucial is the fact that the speed of light in a vacuum is constant and doesn't depend on the movement of the light source or the observer. This constancy of the speed of light is the central point that challenges our perception of time. For light to always maintain the same speed, something has to change, and that something is time itself. When an object moves at very high speeds, close to the speed of light, time for that object passes more slowly compared to something at rest. This is what we call time dilation. In the case of the twin paradox, the twin traveling in a spacecraft approaches the speed of light. As a result, time for him slows down significantly compared to the twin who remains on Earth. This difference in the passage of time, though strange, has been confirmed by modern experiments. For example, atomic clocks placed on planes and satellites that travel at high speeds have been compared to identical clocks on Earth. The results showed that clocks in fast motion lag slightly compared to those that stayed behind. Although the effect is minimal at relatively low speeds, such as those of airplanes, it becomes gigantic when we're talking about speeds close to that of light. Therefore, special relativity is not just an abstract theory, it has real, measurable implications in the physical world. The twin paradox is a clear example of how time, which we once believed to be absolute, is actually a relative and variable measure. Despite being called a paradox, the twin paradox isn't truly a contradiction within the laws of physics. The word paradox might suggest that there's something illogical or inexplicable, but in reality, the phenomenon is fully compatible with the principles of special relativity. The key aspect that resolves the paradox lies in the fact that the twin who travels through space needs to accelerate and decelerate to complete his journey. At first, he departs from Earth, accelerates to a speed close to that of light, and then decelerates when he returns. This change in velocity, or acceleration, causes the traveling twin to shift his frame of reference in spacetime. While the twin who stays on Earth remains in a constant frame of reference, at rest on the planet, the traveling twin experiences different frames of reference due to his acceleration. It's this change in reference frames that explains the time dilation. Time is affected by both the acceleration and the speed at which the traveler moves, resulting in a slower passage of time for him. Thus, there is no contradiction in the twin paradox, only a difference in the trajectories the two twins follow in spacetime. The twin on Earth stays in a relatively uniform state of motion, while the traveling twin alters his trajectory, leading to the time dilation we observe when he returns younger than his brother. The twin paradox isn't just a theoretical curiosity, it raises profound questions about time, space, and even the future of space travel. The implications for science are vast, especially in the field of space exploration. If we can build spacecraft that travel at speeds close to that of light, time dilation could become a practical reality. This would mean that astronauts could travel for years on interstellar missions, only to return to Earth and find that decades or even centuries have passed for the people on the planet. This concept has been widely explored in science fiction. A classic example is the movie Interstellar, where astronauts orbiting near a black hole experience an effect similar to the twin paradox. The extreme gravity of the black hole causes such intense time dilation that, while they spend only a few hours near it, decades pass on Earth. This type of narrative is a perfect example of how physics can be used to create fascinating stories while being based on real scientific principles. Moreover, the twin paradox makes us think about the possibility of time travel. Although it's not time travel as we typically imagine it, time dilation does allow a space traveler to, in a way, see the future of Earth. This concept opens the door to imagining how humanity might explore the universe, knowing that by traveling at high speeds, we experience time differently from those who remain behind. Time dilation can also completely change our perception of interstellar travel. What would be impossible within a normal human lifetime might become possible with time dilation. A journey to a distant star could last only a few years for the astronaut, while millennia might pass on Earth. This effect, while incredible, also raises philosophical questions about the nature of time and how we cope with the idea of aging at different rates. Although the twin paradox might seem like science fiction, its principles already have practical applications in our daily lives. One clear example is the GPS systems we use. The GPS satellites that orbit Earth travel at high speeds and, therefore, experience slight time dilation relative to clocks on Earth. If this time difference weren't adjusted, GPS navigation systems would lose accuracy, resulting in location errors that would grow by meters each day. Scientists had to adjust the clocks on the satellites to compensate for the effects of both time dilation and gravity, which also influences time according to general relativity. This adjustment ensures that the data transmitted by the satellites stays in sync with devices on the ground, such as smartphones and other GPS receivers. This means that whenever you use a map or satellite navigation, you're directly benefiting from Einstein's principles of relativity. Another example is experiments with atomic clocks. By placing two identical atomic clocks at different altitudes or on airplanes, scientists were able to measure time dilation directly. These experiments showed that clocks moving faster or farther from Earth's gravity actually experience time more slowly, perfectly in line with relativity. These examples show us that time dilation, which once seemed abstract and distant, is already part of our everyday lives. Modern science has repeatedly proven that time is not absolute, and the technologies we use daily were developed based on this understanding. This transforms Einstein's relativity from a theoretical idea into an essential practical tool. Throughout this video, we've explored the mysterious twin paradox and how it's rooted in the principles of Einstein's special theory of relativity. We've discovered how time, once thought to be constant, can actually stretch and contract depending on the speed at which we move. What once seemed like a strange and counterintuitive idea has become a fundamental part of how the universe truly operates. This paradox has not only inspired countless science fiction stories, but also has real implications for the future of space exploration and how we interact with time in our daily lives. Einstein's relativity teaches us that time is flexible, something we can warp when we reach high speeds, even though everything may seem normal to us. Now that you understand how the twin paradox works, why not reflect on what else physics has to offer? Perhaps we're only beginning to explore the universe's possibilities and the ways time and space shape our lives. If you enjoyed this video and want to learn more about the mysteries of time, don't forget to like, share, and subscribe to the channel.